Okay, so the next one is 70, exercise 70, and this one is a card shuffling problem. So let's see what the problem says. A card shuffling machine is there that always rearranges cards in the same way relative to the order in which they are given, they are fed into the machine. All of the hearts were arranged in order from ace to king, 13 hearts, and they were put into the machine. So the machine shuffles them once, and then those shuffled cards were again put into the machine to be shuffled once more. And after that, the cards emerged in this order: 10, 9, Queen, 8, King, 3, 4, Ace, 5, Jack, 6, 2, and 7. If that is the case, then in what order were the cards after the first shuffle? After the first two shuffles, after two shuffles, this is the order in which they emerge. So what is the order after the first shuffle itself? So let's see the solution. So we start off like this. Let alpha be the permutation of the cards. The cards means only belonging to the heart symbol, only belonging to that suit of the cards that give the order in which they emerge after the first shuffle. Then alpha square is given. So we need to carefully note that alpha square is given, but alpha square is not just simply these symbols. What these things say here, what this list says is that alpha square is that permutation which gives rise to this order. That is, if the cards are originally put in their initial order in which they appear, that is ace, 2, 3, 4, 5, 6, 7. I have to break the symbol because of lack of space. 8, 9, 10, Jack, Queen, King. Then this new order emerges after running the machine twice. 10, 9, Queen, 8, King, 3, 4, Ace, 5, Jack, 6 to 7. So alpha square is this permutation, and we need to find alpha. Actually, we need it's not exactly alpha that we need to find, but the order in which the cards will appear after just one shuffle. That's what we need to find, and that will come from alpha. So we ultimately need to first of all determine what alpha is. Now let us first of all express this permutation as a product of disjoint cycles. So we start with A. A gets sent to 10. 10. Then 10 goes to Jack. Jack goes to 6. 6 goes to 3. 3 goes to Queen. Then Queen goes to 2. 2 goes to 9. 9 goes to 5. 5 goes to King. King goes to 7. 7 goes to 4. 4 to 8. And 8 goes back to A. That means this permutation is itself a cycle, a 13 cycle, which involves all the 13 symbols representing the 13 cards, 13 hearts cards. Okay, now we need to now find out what alpha is. What can we possibly do? Note this. Now since the order of alpha square is 13. Why is the order of alpha square 13? That's because alpha square is a 13 cycle, and any 13 cycle has order 13. We already know that. So alpha square has order 13. But also recall that we know a formula for finding out the order of alpha square in terms of the order of alpha. So that's why we write like this. Since this is 13, we have, and that formula is this: the order of alpha, the left hand side is the order of alpha divided by the greatest common divisor of the order of alpha and the exponent 2. This should be equal to 30. Okay, now what can this GCD possibly be? Because the GCD has to be a positive divisor of both the order of alpha as well as 2. So the GCD can either be 1 or 2, because 2 is the prime. What happens if the GCD is 2? Suppose that this greatest common divisor is 2. Then the order of alpha will be 2 times 13, that means 26. Okay. Now we have a permutation alpha involving 13 symbols. So that means we are in the symmetric group of degree 13, S13. Now is it possible for an element in S13 to have order 26? No. Why? Because you see, how do we find the element of, how do we find the order of an element in a symmetric group? First we write the permutation, the element, as a product of disjoint cycles, and then we collect the lengths of those cycles, and then we take the LCM of those lengths. That gives us the order. So that means if we do that for alpha, we should get 26. But in order to get LCM equal to 26, we must have either a 26 cycle, which is not possible because 26 symbols are not there, only 13 are there. So, okay, so that means we will need a 13 cycle. Say you consider a 13 cycle, somewhat like alpha square itself. So that gives you 13 in the LCM, but additionally you need a 2 also, and that will come from at least 1 to 2 cycles which should be disjoint with this 13 cycle, but that cannot be found because all the symbols have been used up in this 13 cycle. I mean, whatever 13 cycle that may appear in the factorization of alpha as a product of disjoint cycles. So that is why this order cannot be achieved, it's unachievable. So we just simply write like this: since alpha belongs to S13, this is not possible. That means our supposition is wrong and we are left with only one option, namely that this GCD has to be equal to 1. Thus, we must have and hence the order of alpha has to be 13 itself. And now we can use this information to find out what alpha actually is. How? Like this. You see, alpha can be written as the identity element times alpha, the identity permutation times alpha. Now because alpha has ordered 13, this will be equal to the 13th power of alpha. That will be identity. But now by one of the rules of exponents, this becomes alpha, the 14th power of alpha, which using the other rule of exponents is this. But now we know what alpha square is. It is that 13 cycles. So let's write it here. A10 J6 3 Queen 2 9 5 King 7 4 8. 7th power of this cycle. So we now need to calculate the 7th power of this cycle, and that will be alpha. So at first it may seem like this is going to be big, but it's not. You see, we can calculate it like this. But okay, but before I get rid of this part, let me see if I have written it down correctly or not. A10 J6 3Q, A10 J6 3Q, 295 King, 295 King, 748. Okay. We just need to see what will happen to each of these 13 symbols if we apply these 13 cycles 7 times in a row to them. For example, what happens to A? Where will A go? One application of the cycle sends A to 10, and then 2 applications send that 10 to J. That means A goes to J. So like that we can see at once that A will go to 1, 2, 3, 4, 5, 6, 7. A goes to 9. Then 9 goes to 1, 2, 3, 4, 5, 6, 7. 9 goes to 10. Then 10 goes to 1, 2, 3, 4, 5, 6, 7. 10 goes to 5. Then 5 goes to 1, 2, 3, 4, 5, 6, 7. 5 goes to Jack. Jack goes to 1, 2, 3, 4, 5, 6, 7 to King. Then King goes to 1, 2, 3, 4, 5, 6, 7. 6. 6 goes to 1, 2, 3, 4, 5, 6, 7. 6 goes to 7. Then 7 goes to 1, 2, 3, 4, 5, 6, 7. 3. 3 goes to 1, 2, 3, 4, 5, 6, 7. 3 goes to 4. 4 goes to 1, 2, 3, 4, 5, 6, 7. 4 to Queen. Queen goes to 1, 2, 3, 4, 5, 6, 7. Queen goes to 8. And then 8 goes to 1, 2, 3, 4, 5, 6, 7. 8 goes to 2. 2 goes to 1, 2, 3, 4, 5, 6, 7. So 2 goes back to A. And we should have again all our 13 symbols. Do we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13? Yes. So this is our alpha. That is, if we write it in our original notation for permutations, then we get this A, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. Then A goes to 9. 9 goes to 10. That means 9 goes to 10. 10 goes to 5. 10 to 5. 5 to J. 5 to J. J to K. J to K. K to 6. K to 6. 6 goes to 7. 6 to 7. 7 to 3. 3 to 4. 4 to Queen. Queen to 8. Okay, 8 to 2, and 2 goes back to A. So the order in which you see the cards emerge in the second row, that is the order in which they will emerge after one shuffle. Hence, the order in which the cards emerge after one shuffle is 9A4QJ7, 9A4 for QJ7, Queen, Jack, 7, 3, 2, 10, 5. King, 8, 6. And that's what we wanted to find. Okay, so that is the solution. Let's now see the next one. show that a permutation with odd order must be an even permutation. Must be an even permutation. Okay. So that means in some symmetric group there is a permutation which has odd order. Its order is an odd positive integer. Then we have to prove that the original permutation must be an even permutation. Suppose that's not the case. Let alpha be an odd permutation for which the order of alpha is odd. Okay, so alpha is odd, but at the same time the order of alpha is also odd, contrary to what is being claimed in the question. Then the identity element, which is this, must be odd, a contradiction. Okay, why is it a and how are we getting that this is odd? I mean this power is odd. That's because you see alpha is an odd permutation, and we already know that when we multiply two odd permutations we get an even permutation. And a general statement, a general version of this statement is that when we take an even number of copies of an odd permutation and take the product of those copies, then we get an even permutation. So because our exponent is odd, so an even number of copies, that is order of alpha minus 1. Okay, if we take that many alphas, take their product, that gives us an even permutation, but there is one extra alpha, and the product of this even permutation and that extra alpha, which is odd, but that product is the identity. So the identity permutation must be odd, which is not true, we already know. So that is the contradiction. So knows that I have already run out of ink. I think I should change the marker itself. There is some problem with this. I fed it enough ink, but it's not coming somehow. Anyway, let me feed it some more. Let's see. No such alpha exists, and this just simply this last line is equivalent to what is being claimed. So that is the solution. Let's see the next one. Let G be a group prove or disprove that H, which is the set of the squares of the elements of G, is a subgroup of G. Is it true that in any group this subset H is a subgroup of the group? It is not true. And the counter example is provided by the group A4, the alternating group of degree 4. How? Let's see. Consider the group A4. Okay, now what is this subset H in A4? It turns out that this H consists of all the 3 cycles and the identity element. How? Let's see. Should I write? Okay, let me just write it formally since I have started writing. Note that E square is equal to E, of course, and the square of the product of 2 disjoint cycles is also equal to E, because disjoint cycles commute. In fact, let me just be a little more elaborate and show that this is equal to this square times this square. Why? Because disjoint cycles commute, and transpositions have order 2, so this is also equal to E. Okay. Now what about the square of a 3 cycle, say ABC? We want to actually calculate this. ABC, ABC. So that means first this one sends A to B and this one sends B to C. So that means A is sent to C. Then this one sends C to A, this one sends that A to B. So that means C goes to B. Okay. And then what happens to B? B is sent to C by this one, and then that C is sent back to A. So that means B goes to A. So this is again a 3 cycle. And that's just it. No? I mean, in A4, these are the only types of elements in terms of cycle structure. Identity, of course, will be there, but then we have products of 2 disjoint 2 cycles, transpositions. And then we have 3 cycles, all the 3 cycles. 4 cycles in S4 do not belong to A4 because they are odd permutations. Being cycles of even length, they are odd permutations. Okay, so that means as we consider the squares of all of these types of elements, we end up having identity and 3 cycle. But do all 3 cycles appear as squares? That is another question. No. Also, we need to write where A, B and C are distinct symbols, or just simply A, B and C are distinct. There is D also, so we need to mention D also. These are distinct. Also, if say we are given a 3 cycle, is it the square of something in A4? And yes, it is the square of this 3 cycle. Excuse me. ACB, and let me write another ACB, that is ACB square. Is it really true? Let's see. A goes to C, C goes to B, so A goes to B. B goes to A goes to C, that means B goes to C. Okay, C to B, B to A, C to A. Yes. So from this calculations, you see that what I was stating back then, that is true. Thus, H, which is the set of all squares of the elements in A4, consists of the identity and all the 3 cycles. But this H in A4 is not a subgroup. To see why, you just need to consider the product of these 2 specific 3 cycles. It will not be a 3 cycle. Note that one of them is 1, 3, 4 and the other one is 1, 3, 2. 1, 3, 4 and 1, 3, 2 belong to H, but what about their product? Okay, so let us calculate what this product is. This one sends 1 to 3 and this one sends 3 to 4. So 1 goes to 4. This one does not change 4. This one sends 4 to 1. So 4 goes to 1. So already you see this cannot be a 3 cycle. But let's complete the calculation. This one sends 2 to 1 and this one sends that 1 to 3. So that means 2 goes to 3. That means 3 has to go to 2, but let's see that directly also. 3 to 2 and then this does not change 2. So 3 goes to 2. And this does not belong to H. So H is not closed, so how can it be a subgroup? Thus, H is not a subgroup of our group, that is A4. So that means what is asked in the question, in the exercise, that in general is not true. In this group it is not true, in some other group maybe it is true, we don't really know, it depends on the group. And this is where let's end things. We are going to continue with more exercises and their solutions like this in the next Gallian group update. And tomorrow as usual we have analysis, where we are right now solving problems related to countability. So that's just it. I wrap things up with this. So see you tomorrow with countability. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.